All right, then. So, I'm Emil Fresk. I am the technical manager of the Kite Shield project, and I'm here to tell you actually about Kite Shield, which is a quite long-going project. It's been going for a few years already, and I would like to give you like maybe almost like a slice of life view of where we are today. And hopefully I will come back in years to come to show you how we're going from where we are now, which is in a prototyping stage, where we're to next year going to be more of a switching over to safety critical, and the year after that, hopefully, have been doing safety critical for a while. But Kite Shield. So what are we? What are we doing? But let's start maybe a little bit earlier even. You know, mines. Most people think about a hole in the ground, but maybe I've not thought about it, but it's like the most high technological hole in the ground you'll ever find. It is amazing. But there are things to do here, and one thing is what they call mine automation. And it's about as simple as it sounds, because there's a problem. A mine is as productive as the amount of ore you can extract from it, right? That's what they do, they extract ore. No ore out, no money out, basically. And it's people generally doing the mining. Nothing strange so far. But we have some issues here. We need to blast in the mine, get the rock to come loose, basically. After that, you have poisonous gases. You can't be in the mine, really. After that, you have shift changes, and people have to go out before new people come in, because there's a maximum number of people allowed to be in the mine, etc. So what they found, and this graph is actually now like, I don't know if it's 15 or 20 years old, but it basically pays for every mine automation program in the world, which says that you can bridge gaps in when people do things with autonomous systems, hauling, or other systems. And more than that, at least we from the Swedish mining industry are quite safety focused. So it's also that if you have dangerous areas, you send in the autonomous machines always. So we usually say that it's for the poor guy who got buried in boulders, we want autonomous systems to fill the gap. So let's say that this is the mining industry's aim. The mining industry actually asked their suppliers, like, okay, we want autonomous systems in the mine. Can you please solve this for us? Because there's a lot of different things happening in a mine. And what that actually happened is that every machine that now operates in mines can either be operated teleremote or autonomously. So you could basically say that over the last 15 years, we have gone from, manual trucks excavating ore to actually having a mine full of robots. Quite interesting in its own right. But if you try to just get productivity from all of this, you come to actually a quite interesting problem. We like to call it a thrombosis problem, to make it sound even more dramatic, And it's basically this. There's a problem here. If you were to introduce, let's say, autonomous hauling, that means you have an autonomous truck, which you fill with ore, you drive it up it's called a ramp, it's the road that goes out of a mine to go somewhere, a crusher maybe, to deliver its ore. What you have to do today is that all the path this machine needs to traverse, you must close it off. No humans are allowed in there. And we call this basically robot cells. It's quite common in manufacturing industry. You box in the robots, basically. But if you have a mine where the majority of the time goes to extending the mine, maintaining the mine, pulling cable, putting up Wi-Fi access points, telecom equipment, everything. If you close off a mine like this, it will ground to a halt. It doesn't matter how much autonomous machines you have, it will not operate at all. So what they do today is that they only put them in the green little box. Just out where you can dig the ore, there they use teleremote and autonomous systems today. Everything else is almost non-utilized when it comes to autonomous systems in mining. So you could think a little bit like, how do we make humans and robots coexist in the mine? Because we have a problem. If we just let people into these robot cells, well, this is basically what's going to happen. Either humans will drive into the robots, more likely, the machines that move this rock is 100-ton machines. When they drive over something, they drive over a pickup, there's nothing left. But there's not even a scratch on the hauler. They just crush things. So maybe the pickup will do some damage on the robot, but probably not. And, This is how we solve it. We lock the robots in. So, not that flexible. So one could then maybe start asking, well, what is actually the problem that we have here? And the problem is, as you might have seen from the theme of this conference, it's a functional safety problem. We cannot guarantee the safety of people who operate close to these machines. And our threat model is basically, if you touch it, you die. That's the threat model, which makes some interesting argumentation, but it makes, it makes some interesting discussions, but it makes argumentation really simple, because you don't have like exposure, which is also a common knob you turn to do things. And this is where sort of we come in, because the mining industry has had this problem for a long, long time. They have tried to get the suppliers of the mining industry, which actually makes these huge machines, to solve this problem. And they have not really solved it. They still go with robot cells. They try to build like their own silos of their own proprietary systems, and in there you can get better than, well, if you try to mix them, one might say. But the mining industry, they want to be able to mix humans, and in this case we will usually say manually driven machines, usually not people walking around. That's a problem of its own. And we want to mix them with autonomous or teleremote machines from different vendors. So there's no lock-in effect. So the mining industry, after many years of trying to get suppliers to do this, they realized they're not getting through. So they were like, all right, we're going to solve this ourselves. So that was part of the introductory slide. We have now 3 mining companies, 2 Swedish ones called LKAB and Boliden. They are like the founders of the Kite Shield initiative. And then we have BHP, who is the 3rd mining company to join, which basically funds this entire thing. But it's then we could call it technology organizations, which do the work for these mining companies, where Kite Shield, where I'm with them, is part of. So, what do we do? Maybe we have at least a problem that's sort of understandable. Well, the problem we need to solve is surprisingly simple to explain, isn't it? You could say that we only need to guarantee that an autonomous machine, or an automated machine of some kind, is not at the same location as a human or a manual machine at the same time. If you say it like that, it sounds almost trivial, right? A lot of people spent a few years in the beginning of the project figuring out, safety integrity levels for different parts of the systems and everything. But if you were to just do a broad statement, this is a system that in the end, as a whole, needs to achieve SIL 3. All right. So how do we get there is like the big question, right? And when this project was in its early phase, you could say that, well, we want to build a system that's safe. All right, how will we approach this? Well, there are, technically 3 ways. We are building something new that does not exist. So we cannot stand on standards for part of the system. Of course, we will follow normal, functional safety development practices and all this for that, but there is a part of the system that is completely new, that has no standard on which we can stand. And then you have basically 2 approaches you can do. Either you try to crack it with statistics, or you try to crack it formally. We did the math, trying to figure out how long we need to run our system to crack it statistically, and it was on the order of 114,000 years. So we sort of thought that was a little bit too long to wait 114,000 years to get the system into production. So instead, this is a system that builds purely on formal motivation all the way up to the measurement. And I should say, the mining industry, when it comes to safety, is a very conservative area. If something new comes, they are highly skeptical to almost the extreme. So we also saw it that the only way to get this to be accepted by this type of industry is to go in a way that you cannot refute what we're doing, that everything that is new is formally proven. And also as part of this, we kicked off a parallel thing that's more of a side note maybe, but it's quite interesting. And it is what we like to call proven safety, and it's being driven as part of the Global Mining Guidelines Group. And then they call it GMG, there's a G missing, I don't know why. But they are basically the ones that set standards and guidelines for the mining industry. Safety, technological, even mining methods, they do everything. And because there are ways to do it if you see how you usually build up claims or safety cases. So we basically wanted then to go like basically, an axiomatic approach. So we were then said that in this type of argumentations we do, that we always want to favor, like measurable safety over subjective judgments, defined limited context or vague contexts, arguments over claims, and the one that is a little bit funny, but if you want to talk more about it, we can maybe talk after, is like how you can use valid societal moral concepts outside the definition of risk. And this is quite interesting, because what we're building anew in this, you could maybe call it the secret sauce of this kind of a system. And this is being published as white papers in GMG. So everything that we are doing for this system will be fully open, the theory behind it, the mathematics behind it, motivations behind it, and the next white paper is how you implement it in practice, on what radio technologies you need to use, etc., which I'm going to show you today, which is the prototype that actually builds on top of these foundations that were set earlier in the project. But it's easy to try to talk about what we're doing, but I like to show instead. So before I start, it's a video I'm going to show you, is that when I say a robot cell, if you want to visualize something yourselves, what you can do is think that take a part of the mine, draw a box around it, and say that anything that touches this box or goes inside it will cause the entire automation system to stop. All machines will stop. Easy? Not that flexible, because to enter this box, you go through it's like 3 laser barriers. You go through, and it's like a dance to go into it. But what we are doing instead is based on top of a little bit of new radio technologies that have been surfacing. We can make formally provable volumes of where something is inside a mine. And basically, what we can say, if we expand these volumes with machine size, stopping distance, etc., is that we can basically form a proof for how you make a safe stop maneuver that is verifiable. It's 100% verifiable. And this is a nice rendering of something in, but of course we have demo systems running in multiple mines right now for the ones who want to run. So this is actually from one of the demo systems running. So the yellow is the provable volume that this system builds everything upon. And then there are some examples basically on how you can add machine footprints to this kind of safety volumes, and then how you can add safe stop distances, communication delays, everything into this to basically form these kind of, I like to call them safety bubbles, because it sort of explains what they are, but some might call them the localization bubbles. And then we have some, of course, problems. You need to be able to pass autonomous machines and all this. So, if anyone has talked about like dynamic geofencing, this is basically dynamic geofencing, if you want to have a different view of it. And one of the final highlights, let's call it, is we have 2 actual machines driving towards each other. And since this is not, certified yet, we have basically LEDs blinking the driver in the face when he's supposed to hit the brake. So, if you want to do something. Yeah. But the question is, of course, we are saying that, well, if we do this kind of a thing, that we can actually improve productivity of an autonomous mine. That's like the entire claim. Else the mining industry would not be funding a project like this. So we actually have a first installation area I'll talk a little bit about, just to show that there's some value to the claims I'm making. And there's basically a new mine. It's called Rävliden. It is a tiny satellite ore deposit from a real mine today that's called Kristineberg. In Sweden, it is practically impossible to get a new mine permit. So if you find a new mine close to an old mine, how do you start digging that one out? You dig to it. So from the old mine, they create a straight tunnel that's here in light blue that goes from an old mine all the way to this new ore deposit that's 700 meters below ground. But here's the problem. When they designed this mine, which was 15 years ago, the business case was built on the assumption that the problem of having these autonomous machines running, it will be solved in 15 years. So for this mine to be profitable, they need these autonomous hauling systems that people can sort of pass through. And here we are. Do you think these systems exist today? No. So it also is a sort of a motivator for them to assist us in this. But the interesting thing here is you can either try to section this up into multiple check-in, check-out stations. You can make small robot cells, but that's absolutely horrible from a user's perspective. It's easy to get wrong when you need to check in, check out a lot through this type of zones. So the only considered valid use case was that you put a check-in at the top, a check-out or check-in, check-out at the bottom as your robot cell if you're working around a robot cell. Or we could compare that to Kite Shield. So a lot of simulations were done to show basically the difference. And what we show here is that without Kite Shield, we have on the bottom how often someone drives in manually with a pickup in the system and the utilization you get out of the automation systems. So, if you only have a human coming every 30, 40, 50 minutes, it's quite okay to have a robot cell. It's quite okay. The problem is that the normal entry rate is about every 10, 15 minutes. That's when someone goes in to do maintenance, do something, need to traverse the area. However, with this type of geofence bubble systems that we are working with, you can say you get a little bit better, to say the least. And what we then do, basically, if we want to see it more from a very high level, is that you could say you have Kite Shield, and we do integration with the autonomous machines, so we can pull their emergency stops, and we do integrations with let's call it all other vehicles in the mine, such that they can be tracked in this system. Because in the end, we need to know everyone that operates in this system to be able to form these volumes. If someone is a ghost in the system, that's basically someone that will be run over eventually, because these machines will not stop unless you're protected by this kind of system. And then we have some other things where we are we are a safety system. We're a safety system only, but we generate enormous amounts of positioning data from this type of system and other information. And it's basically that on the top, we will provide all of this data free of charge for anyone who wants to build applications on top of this type of data for the mining industry. Because that's also a big problem for them, that they get basically closed in, or they get proprietary solutions. The sharing of data is not really there. And we're a safety system, so anyone can have our data. But where are we today with all of this? You could say that the research was done. It was about 2-3 years of work prior to starting prototyping, where we did basically analysis of the safety cases for this thing, tried to make the scenarios, figure out which part of the system needed to be to what safety levels in the end to be able to make a formal or make the final motivation. And where we are today is what we like to call advanced engineering. I would say prototyping is more I would say the correct word. But we are aiming that second half or around summer next year is the plan that the current prototyping team shall be finished the training to transition into a safety critical product team. So we are halfway through advanced engineering. And with that, I'd like to give you a ride down to what we actually build, the actual system that is being built that can produce these type of safety bubbles in the end. So basically what we build for the mining industry is an infrastructure. So we just for today, we'll call it the Kite Shield infrastructure. But basically what it is that we put up radio devices in mining tunnels, which can measure the distance to other devices mounted on vehicles very accurately. And then basically we'll have, instead of saying this distance is correct, we consider that every distance will get a lower bound. Because thank you to the speed of light, and hopefully no one will break that very soon, we can only get too long measurements from the type of technology we're using. We cannot get too short measurements. So with this, you can form these type of volumes. But we have quite interesting technical requirements if you want to build a system like this. And it's based on a radio technology. If anyone wants to Google it later, it's just called ultra-wideband. It's in your phones, it's in your car keys, it's in cars. It's quite everywhere. And we're actually basing it on chipsets that are for car keys, together with NXP, who's helping us certify these chipsets to the required level that we need. But it's enormous systems. We talk about up to 100,000 network-connected IoT devices. This is what we call the infrastructure. Over up to 1,000 kilometers of mining tunnel. This is the design goal for this kind of system. So it's not one device somewhere. It's an absolutely enormous system. We have some quite high requirements, some time synchronization as well, and robustness. But these are more like things that comes out to be able to utilize radio efficiently. So if you want to give it a very high view, you could say that we are building a cable. That's what we are building. You get a cable with tiny molded plastic blobs on it. Inside these plastic blobs is all the radio technology you need. If you pull this cable out, that's 250 meters. You hang it up. Well, you put two of these cables in one mining tunnel, one for redundancy. You have then covered 250 meters of mining tunnel with this type of system. And it's basically based a lot around how they do maintenance today in mines. So it's actually a real thing. So it does not look at the render, when render meets reality, one might call it. And it's basically let's call it maybe not a dance, but quite a lot of different radio technologies working together. So it's basically one radio that's used to measure the distance. This is what we call the ultra-wideband radio. And then we have a whole bunch of what we call out-of-band channels, which are used for communication links, but not measurements. Even though you can send data with ultra-wideband link, we really don't want to use the ultra-wideband link for data transfer, because that's measurements we are losing by spending time sending data with that radio. Plus, we're using multiple different radio technologies and frequencies, because how radio waves bounce in tunnels, you get Fresnel zones. So that's when you have nulls, when you don't get any reception with carrier wave radio. So by having different frequency and the different modulations, we get that these extremely seldom overlap. And for the ultra-wideband, which is a pulse radio, you don't even have this effect. So it's quite neat. If you want to give this a little bit more of an high-level overview, you could say that an anchor, this is the device you mount on the cable. It's basically an Ethernet switch to ultra-wideband converter. I mean, that's basically what it is. But it does some things in there as well too. So we can have provability in our measurements. Who was it talking to? How do you know that this one actually measured with that tag on that vehicle and not some other tag? How do you not know that one tag is not spoofing another tag? It needs to do some kind of work to do these kind of proofs of where data came from as well. But other than that, it's basically to relay this radio communication. And if you want to give it, if we zoom out to an entire mine, it's a little bit much, but just to give you an idea, in the center you have these anchors, we call it. So you can think that there can be up to 100,000 of this center part. At the bottom we have tags on vehicles, and there are what we call heartbeat endpoints, proof of existence loops, you might call them. But the tags are very few in this system. If we get up to a few hundred, it's an absolutely enormous mine. And this is quite weird, because if you look into real-time localization systems built on this technology, you will see quite quickly that every system is built for the opposite thing. You have thousands and thousands and thousands of tags, but you want like 5 infrastructure points, because infrastructure is the expensive part. But what we have done to make this attractable for the mining industry so that we'll place it everywhere, you can't have expensive infrastructure. So even when you take, that the finished certified product, it's going to have a comparable cost to copper cable to put up in a mine. So it's not that you make this hardware that's going to be super expensive, they'll put it in 100 meters where it's a huge pain. No, we want them to deploy it everywhere. Where they don't use it for safety, we want them to use it for asset tracking or other uses. But they could use it for safety critical applications later. And I had one video showing that's more like the classic use of this type of technology, which you would call real-time localization systems. You have probably seen this. It's that this kind of radio technology, it measures distance quite accurately, so it's quite easy to do triangulation with this type of radio technology. Just to sort of drive the point a bit that measuring distance with this type of radio, it's quite accurate. In this case also you can see like the squares is where we put these anchors, as we call them, the infrastructure, and the spheres then my colleague Didrik here walking around with a tag in his hand. And so far, this is a Rust conference, right? We have not really talked that much about Rust. But you might have been guessing on what we build everything in this system on. And we are, building a high reliability system. So we are building this on everything on Rust, basically. All tooling, all software, all firmware is written in Rust. The things we can't really get in Rust and have problems with, we reverse engineer from the manufacturers and re-implement. We've had quite a lot of problems with different weird debugging protocols that we've not been able to get documentation for example. And even more internally, we also run as the foundation for this, we're actually running Arctic. For those who have not heard it, it's the hardware-accelerated operating system for Rust embedded. I'm the maintainer also of Arctic, so I have to chill it a little bit if we're here. But something that makes me really happy that we're working with the mining industry is that even though we can work with Rust and all of this, but we also actually get permission to open source these things, which I'm very happy about. So we are helping extend some of the processing ecosystem around what we're doing, helping extend ProbeRS, which is how you talk to debug probes in this kind of area. And just as a maybe final note on how we use Rust in all of this is that what we're building today is a prototype. It is not designed to be safety critical. It's that we want to verify the performance, we want to verify the robustness. We're basically building a functional specification that once this thing works, we shall re-implement it into a safety critical product that works the same and has the same performance, the same robustness. And as part of that, I have a small tidbit on Arctic's journey towards safety critical. And today it's a huge monolithic code base. If you ever go in there, you'll get almost lost in it. It's that kind of a size of a code base, which is not maybe great. So currently we're actually working a little bit on splitting all of this up into what we call modular parts that can be composed. So you can take out the tiny, tiny, tiny core of this if you want to use it in safety critical, or you can use the big thing if you want a nice user experience, but then you also have to live with it maybe not being certifiable. And this is being done actually as part also of research projects together with the local University of Technology, with one of the professors there who is like the godfather of this operating system we're building. And with this, it was sort of like a slice of life where we are currently in the Kiteshield project, of where we are in everything from, I should not say that from a safety critical point of view, since this is about to start in-ish 9 months, so to say, but also where we are in prototyping, that how you can move forward and that you want to show to the mining industry with working prototypes that this system is possible, it will reach the performance they need, and it will also actually do what we promise. So building the confidence between them as the stakeholders then and us trying to create this new technology for them. And I think I'll actually end with that and take questions.
Thank you.
Thank you.
I see a very eager hand in the back already.
Thank you for the amazing talk, first of all. My question is about the formal verification. Mm-hmm. What kind of methods did you use? Like, this was worked out by some mathematicians, or have you used formal verification tools like ROC, for example?
No, it's actually formal in the sense that we build it. You could say that we have a deep theoretical foundation in what we're building. So to be able to show that all the way up to the measurement that we build on how you can form these volumes, because that's basically what we need to show. We need to show axiomatically that these volumes, if they intersect, we have a dangerous situation that's about to happen. But then we also basically have to prove all the way down, assuming we can do the measurement, where measure theory comes in as part of this, that it holds. And well, if you want to know more details, we could talk a bit more maybe. But it's basically everything is built as one large mathematical proof, from all the way from choosing your number system through relativistic physics, all the way down to how we should implement the algorithm to make sure that this will work. And there we are not actually sure of will we use formal methods to also implement algorithm? Because it's basically, in the end, you see nice bubbles in these examples. In practice, the volumes are blocks. So we don't know, it's probably you will do that also using formal methods, because comparing block intersections is not that hard, basically.
Thank you. I have another question. Is that you've only mentioned like mineshaft operations, but is this product applicable for surface level mines also?
For surface level mines, technically yes, because as usually, the example with them going out of a mine with hauling, for example, you don't want the safety system to end at the entrance of the mine. Where do they take the ore after that? The system has to extend outdoors to like the crushing areas or where they dump for storage, things like this. But also outdoors, there are some systems already on the market today that are GPS-based. It's just that the bubbles are a lot bigger, but it's basically the same idea, that are GPS-based, that have gone through safety certifications already. If one wants to Google, there's a mine called Aitik in northern Sweden, where they're running a system from Komatsu. And this is basically the same idea, GPS-based, but they're running it on these 300-ton mining trucks, the ones that are the size of buildings, basically. But then they're running these trucks autonomously. So there's maybe some overlap, but more interesting would maybe be other areas where humans and robots work together, and it is a limited set of things. Warehouses with autonomous robots, someone still needs to go in there and do maintenance. Harbors, you have autonomous cranes. Smelting plants, you have autonomous gantry cranes carrying molten metal. These are perfectly applicable to this type of a system in the end.
We have a question over here.
Yeah, I'm a mathematician, so therefore, a mathematical question here. Let's assume you have now proven that the system is correct. I would assume that the proof is multiple pages long, maybe hundreds of pages. Well, therefore, if you go now to an assessor and he's not a mathematician, has a, let's say, 1 year time, he just has to believe you. In the end, nothing. So therefore, how do you ensure that your proof is actually correct and that you don't have a little sign mistake or something like this?
Yeah. I don't think we have a method today to do that. What we basically did so far is that the proof that all of this builds on, we have a colleague of ours. He used to work at the assessor that we were. He worked for 15 years, and he was their mathematical proofs guy, so to say. And we recruited him to us to help us form and build the proof in such a way that, with his experience, we hope it will be easy to get it through. But the nice thing with this proof is that every small step in it is, it's not, you write one big proof, everyone is like a small step, you make a proof there. You make a small extension step, you make a proof there. So in the end, it's I'm not sure if it's be a problem. I have no idea, to be honest. But that is our approach to the problem. So you take these small steps and make a proof. You take a small step, you make a proof. And use that as a building on each other. Yes. Or it is being published in like 2 weeks. Okay. Yeah. But it's like 20 pages. Okay. Ish.
Okay. Well, thank you, Emil, for closing out this conference and
thank
with
you.
your great talk. Thank you so much.